All right, how do we change milliliters to liters?
Draw a chart.
Draw a chart. Now, this is one of the things about the gas laws. You have to be able to do these conversions. They are spread throughout every gas law problem that we're going to learn how to work. If you can't make these conversions, you're going to crash and burn quickly, okay? Because every time you convert it wrong, and every problem, it's a standard deduction at this point, okay? If you do it wrong, and every question on the quiz, you convert volume wrong, for example, it's a 5-point deduction, okay? Every time. I don't care that you did it wrong every time. So you've lost 25 points off the top and all 5 questions. Is everybody with me on that? So if you can't make the volume conversions, you either need to get together with a friend who can show it to you, or you need to come see me for help. But you need to learn how to do it. Everybody with me on that?
Yep.
Okay. She needs to ask somebody if she's checked out to lunch again over there. So, King Henry died by drinking chocolate milk is the conversion that we learned way back in the very beginning of the semester, right? We learned to draw a T-chart. 160 milliliters went on the top. Where do milliliters need to go? Bottom. Liters went on top. Who was bigger, a liter or a milliliter? What went beside it? And how many spaces between the liter, which was on the baseline, and milli at the bottom? 1, 2, 3. So that meant what? 3 zeros. And then we put a 1 in front of it. So if I were you, and I didn't want to draw that all the time, we're going to use milliliters so often, I would memorize that milliliter is 1,000. Okay? So 160 divided by 1,000 is what? 0.16 milliliters. Now, I will tell you that as long as your significant digits are within 1 or 2, I'm not going to beat you. Oh, liters. Thank you. As long as you're within 1 or 2 significant digits, I'm not going to beat you up about significant digits. You've learned how to do significant digits. They're not on the exam. Okay? So, as long as you don't write every number on that calculator, you're within 1, I'm going to be happy. All right? What do you know about centimeters cubed milliliters? They're the same thing. So, 5.34 milliliters. Now, 57.3 grams, we're going to moles. Grams to moles. What do we know about a mole or a gram?
Has a 1.
Has a 1. We don't have a balanced equation there. So we don't need a coefficient. We're just going grams to moles. What's the mass of oxygen?
16. Right? No? Maybe not? Okay.
Maybe not.
32.
Why?
Because oxygen is O2.
Oxygen's formula is O2. It's one of the 7 diatomics. So its formula is O2. So its oxygen's mass is not 16. Okay? You do have to remember the diatomics because oxygen does not exist by itself. It's just O. It's O2. So you've got a mass of O. It has 2 atoms times its formula is 16. So 2 times 16 is 32. So 57.3 divided by 32 would be what now? 1.79.
Those 7 would be having 2 on those 7 elements.
Say what now?
Those 7 elements.
Yes, those still exist. Yes. Yes, ma'am.
So we don't have to do that for all the diatomic.
All the diatomics. That is correct.
And that's that hectare now.
5 clear brown iguanas. Yes. Okay. And Kelvin to Celsius, what's our formula?
C plus
2. K equals C. And if you've forgotten it, where can you find it? On your blue chart. So K equals 34 plus 273, and you get 304. And then K at the end. Remember, you got to put a unit on it. The first K that says K equals is just the variable. You got to write the K at the end. Questions about how to do any of those conversions? Are you okay with that? Good. Now, we need to run through the notes that you guys watched on Monday. And I apologize for having to go through it again, but unfortunately, your sub did not hand you the note sheet that was supposed to go with the notes. Did you take any notes?
No.
You just watched the video.
I watched it, but I was confused because I was like, why does it say November 2000?
Because it's the same lesson we're going to do today.
I only watched
You were-
like 10 minutes of it.
I know. You were supposed to get a note sheet that went with it. It's today's lesson.
She didn't do it. She didn't.
I know.
Bad.
I know.
That's
It's okay. It's okay.
Not.
You were playing for that to happen, weren't you?
It's all good. This means we
We
have
got
to.
used to more bath with this unit.
Now, today's the only day that we're taking notes that are really words other than mouth problems, okay? Everything after today is word problems. Mhm. And this is the part of the test that the multiple choice comes from.
What is it?
The test will be, best guess, sometime late next week. Middle to late next week. All right, it's not the wrong one. Here it is. All right, and the test is 10 multiple choice questions and 11 word problems. Mhm.
You said 10 multiple choice.
10 multiple choice and 11 word problems.
Okay, let's look at
All right. KMT, or kinetic molecular theory, is the idea that the particles in a sample of matter are always in motion. All right? If you're running out of paper or room already, yes, you are going to need a bigger notebook before the semester is out. We have a long way to go.
Oh, shoot. I should have bought one of them. Should have bought one of them 5 subject finals. I mean, no. That's what I don't know. You gotta wait for it.
Now, we talked about, when we talked about bonding, the 3 types of motion that all particles have. All particles are able to rotate, they are able to translate, and they are able to vibrate. Okay? Now, gas particles, because we're talking about gases, do all 3 of these things. Now, given we just talked about this, hopefully you remember what those things are. What does it mean to translate? What do you mean by slide? So when you get up to go to another period, you're going to do what?
Transition.
You're going to translate. When I walk from place to place, I use what kind of motion? I translate. That's the only kind of motion this wall has. Okay, I can't rotate, and I generally don't vibrate. All right, rotational would be what? Spinning. All right, and vibrational would be what? Vibrating, shaking. Okay, if any of you have relatives, or generally, this is something that happens to older people, who have Parkinson's or something like that, they will do what?
They just shake.
They shake.
That's right. Okay?
I have a question.
Yes. No, but I would imagine something of that line.
And Miss Beaker had that?
No.
Miss
but
Beaker was
yeah,
shaking.
No, she used to just do like this. I ain't know what that was.
It's not, but I would imagine it's something of that variety. So, well, she's on field trip. All right. So, when does motion stop? If you remember, I think we talked about earlier in the semester, it stops at absolute 0. So, when is absolute 0? Do you remember what that number is? Anybody learn about another science class?
0.
0 what? Huh? Yes. Absolute zero is defined as 0 Kelvin. Okay? 0 Kelvin is the definition. Now, absolute zero is defined as 0 Kelvin. Now, no one in this room has any idea what 0 Kelvin is. So to give you an idea of what 0 Kelvin is in terms of a number, I gave you 2 other numbers so that you can relate to what it is. All right, 0 Kelvin is negative 273 degrees Celsius, for those of you who are familiar with the Celsius scale. But most of us in here are only used to numbers on the Fahrenheit scale. So on the Fahrenheit scale, that would be negative 457 degrees Fahrenheit. Now, at negative 457 degrees Fahrenheit, motion will stop. Believe it or not, your desk right now has motion. The particles in your desk are moving. Most of you don't believe me, but on the geometric level inside your desk, the particles inside that desk are vibrating. When you're dead, laying in the casket, if you choose to be buried, are the particles inside your body moving? Yes, they are. If they weren't moving, could your body decompose?
No.
No. If we dug you up 10 years down the road, you would do what? Still look as good as you did the day you were buried.
That'd be cool.
That would probably be very cool. But are we going to look the same we do the day we're buried 10 years down the road? No, we're just not. Even for our bodies to turn to absolute ash?
No, just like
Years. Years.
like 2 decades.
Yeah, probably so.
So why can't we feel the desk vibrate?
Huh?
Why can't we feel the desk vibrate?
Because we just can't. Okay? Those particles are really, really tiny and they're vibrating. Now, if you ever watch like Bill Nye Science Guy and you look at like liquid nitrogen, okay, that's getting close to absolute zero, but it's still not at absolute zero, okay? But it's getting pretty cold. Now, we're in a first-year chemistry class, so we're going to try to look at something that's easy to calculate. So, first of all solids, liquids, and gases have motion. I point this out because what do you think students get wrong on the test? What do you think they leave out for me on the test?
Gas.
No, solids. Justice is right. And even when we take this test next week, even though I just put that there and I just told you that, people will still get this question wrong on the test. And they will still tell me that what state has no motion.
Solids?
Mm-hmm.
Oh, I understand why they think
I do too. Okay, and it's very difficult for students to come to grips with the fact that solid particles have motion. So, if I go back, what are the only kinds of motions that solids have? Out of these 3 types, what's the only kind of motion solids can have? Vibrational. They can only vibrate in place. They don't translate. The desk particles inside the desk cannot move around. Okay? They can't spin and rotate. They just vibrate where they're at. But they do vibrate. Okay? Now, you do not need to write that. This was done for a sub years ago. So, we're in a first-year class. So, because of that, we're going to study ideal gases. Okay? If we were college level and we were chem majors, we would study real gases. And that's multiple classes in as a chem majors. But we're going to study ideal gases. Ideal gases have to obey all 5 assumptions of kinetic molecular theory. So, what are these 5 assumptions? Now, I'm not going to ask you to list the 5 assumptions. I just want you to be able to tell me which one doesn't belong, for example, in multiple choice. And I am going to ask you what conditions the gas would have to fit an ideal gas. Because our word problems are going to be ideal gas word problems. I think that's all I have on that screen. Everybody caught up?
No.
That's why. I'm sorry.
No, I'm just worried about the refrigerator in my place. That's all. I mean, they're in power strips, but you know, I don't want to lose
She
my
still ain't put it in her
refrigerator.
essay grade. She still hasn't put it in her essay grade. And I emailed her last night, I was like, I'm gonna.
All right.
You're trying to figure out your questions. She was like, I'm sorry. I was like, well, you could at least told us which ones was wrong. Like, how are we supposed to look at the test and know which ones are wrong and right if she didn't tell us?
All right, so what are the 5 assumptions? Number 1, we're going to use a gas that has a large number of tiny particles. Well, how are we going to use a large number of particles? Well, if I was to use a gas problem that had 1 mole, how many particles would be in 1 mole? I know y'all didn't just say 1.
237. Particles a lot. No.
What's the question?
I said, how many particles are in
456.
mole?
123.
Sweet baby Jesus, y'all better start looking up the prices of alpacas. Because I need to buy some and get out of this job and go find me a farm.
Alpacas make good money.
I don't know, but apparently I might be better at raising them than teaching.
Not either one or a lot.
Because clearly I suck at this job.
It's 2.
Y'all can't tell me how many particles are in a mole
It's 5.
after 57 days in here.
You never tell us.
6.0.
There is one soul who has an idea. Thank you, Justice. Thank you. Just thank you.
6.022 to
10 to the
Oh,
third.
the
I'll put,
I was
yeah, I chose that. Yeah, I got it.
No, you did. You would have said it. You
Well, my
would have
mom
said
was
it.
like,
See, it's never that deep.
It isn't. One mole of particles has that many of anything. It doesn't matter if it's an atom, if it's a molecule, if it's a formula unit, but 1 mole has that number of particles. If I asked you for 1 mole of eggs, it has how many?
See,
Avogadro's number of eggs. Okay?
apples don't.
If I wanted a mole of cookies, you would have how many cookies?
This many.
That number of cookies. Okay? It doesn't matter. 1 mole is that number. Okay? Whew. All right. All gases are going to move in constant motion, and they're going to be in straight lines. That's not hard. All right. All gases are in straight lines. They're not going to walk up to some other gas or move across the container and go, "Ooh, excuse me, let me go around." All gases are in constant motion, and they move in straight lines. If a gas gets in the way, what do? They do what? They just bump it. Thank you, Tiffany. It's a lot like walking down the main hall in the high school. Something's in the way, they just shove it out of the way. Exactly. Number 3 is a new vocabulary word for us. All collisions are elastic. Okay? This is a new vocabulary word. Yes, we do. All right. Elastic collisions means there are no net loss of kinetic energy. It's transferred. So, if, let's just say that Tiffany runs into Jaden in the hallway, all of the kinetic energy that Tiffany has is transferred to Jaden.
No, why are we gonna give her all the energy?
It just is. Okay?
But she's
It's
weird.
not lost in the form of heat or anything else. All right? If Jaden runs into Tiffany the next time, all of Jaden's energy can be transferred to Tiffany. Okay? It's not lost in the form of heat. All right? Now, in the real world, is all the energy transferred from one molecule to another?
No.
No. All of you guys have probably watched a pool game or seen pool on TV, even if you haven't actually physically played pool yourself. If you've watched pool balls hit each other, does one ball hit the other ball and then one stop while one continues every time? No. Okay? In this particular setup, that's the way an elastic collision would work. All of the energy of one molecule transfers its energy to the other ball, or the other molecule. It doesn't work that way in real life.
Is it
Okay?
like, what's that one model where we like, when you let it go and it's like, is
That's a Newtonian collision model.
that like,
Yes, very similar to that, okay? But again, some of it would be lost to friction and other things, but we're saying that doesn't happen. Okay? Number 4, all right? There are no attractions or repulsive forces between molecules. Molecules are not going to attract each other. They're not going to repel each other. So the only way they can do that is if we have the absolute weakest molecules that you can have. So we're going to say they're non-polar.
Tiffany, if we don't have a partner, how are we supposed to know, like, what we got wrong and stuff like that?
I don't know, she was just like, you're supposed to compare it with other people and see what they have, and then figure out which choice is right or wrong. But like,
But how are we supposed to figure it out when
We
we
don't
call
know.
somebody over if you're on or something?
she said we're supposed to figure it out based on
You're supposed
other
to be
people.
able to back up your answers to get it right. That's how she did it with us.
I got a 79, so I'm only gonna do the last 15 that I didn't answer.
Right.
You have to be able to
That's
back
fine. I'm only correct.
I think I'm
All right.
And I mean, it's not wrong on that.
Cause then I'm gonna mess around and change one of the answers that I got right.
She's not gonna count. I'll figure it out.
All right, last one. The average kinetic energy of the particles depends on temperature. What's that mean? That's an easy one.
you said that.
So what's number 5
If
mean?
it's super hot, then I was able to, yeah.
If it's super hot,
and fast.
they move faster. Okay, that's right. So the higher the temperature,
Higher temperature, more motion.
that's right, higher temperature equals more motion.
More motion in the ocean.
Okay? The more temperature you have, the faster those particles are going to move. And it's not just about gas molecules that do that either. You know this yourself. Particularly those of you who are athletes or those of you who exercise in any way. If you move around more, what do the particles in your body do? They move more and you have the sensation that you feel hot. Okay? So the more motion you have, the more your particles move, the warmer you feel. Whoops, that is not what I meant to do. Hold on. I think I can fix it. There you go. I did not mean to extend the page repeatedly. All right, does everybody have it? All right. So, everybody got it?
Yep.
All right, we're going to talk about what conditions we need in order for these things to happen. How do we get these things in a gas law problem? Okay, how can we get those? Number 1, our gas law problems are going to use non-polar molecules. That's not hard. All right, we'll just work gas law problems with non-polar molecules. The second thing that we will do is we will work problems that have a higher temperature. We just won't work problems that have low temperatures. We won't work problems that have negative numbers. They will generally be positive number questions. And we will have low pressures. The reason is we want the molecules to stay far apart So, they,
Ms. Wall,
yes,
when is a good time? I need Justin YAM
okay,
come to guide us for just a moment.
okay. They trying to give me a heart attack?
Is it scary?
Yes. But right now, anything startles me the way I feel. All right. So we want the molecules to stay far apart so they can't attract. So if the temperature is high and the pressure is low, the molecules are not going to get close together because with a high temperature, are they moving fast or are they moving slow? They're moving fast, okay? So they can't attract. But if they're moving really slow, it's likely that they can attract one another. So you want them to be moving really fast so they can attract. Now, the reason I don't want them to attract is which one of these things said you don't want them to attract? Number 4 said we don't want them to attract, right? So that's why we want them to stay at a high temperature. Does that make sense? So all we have to do is work word problems that are nonpolar and they have a high temperature and a low pressure. That's not hard to do in a first-year class. So it's not like all this stuff that said it's an ideal, it's sort of imaginary. It's not hard to make up word problems that fit those conditions. So don't think we're making up problems that really don't fit stuff that's all imaginary. And you're like, why is she making us work these fake problems? It's not that fake. Okay? So what's a real gas? All right? A real gas just doesn't obey the 5 assumptions. And they're ones that really exist in nature. Okay? So, real gases, all right, real gases are gases that do not obey the 5 assumptions, and they exist in nature.
Ms. Wall,
Yes, ma'am.
Ms. Moore, can you send me work for J Peoples if I'm not in here? Just had a student to leave it in my basket in the door.
It's the same as Brooks, Miss Moore.
Bruce, okay, I'll make her copies.
Sounds great.
Okay, thank you, Ms.
You're
Wall.
welcome.
Working ISS.
Mm-hmm.
I'm good. Let me take it to him.
I already sent it.
Oh.
First period. All right, everybody got it?
Yes.
All right, so if I said, what conditions for a real gas? And I didn't give you any conditions, what would you do?
What we assume?
What would you assume for a real gas?
They're polar,
They're polar,
they're low temperature,
they're low temperature,
they have high pressure.
they have high pressure. All right, so can you give me an example of a nonpolar molecule based on what we did in the last unit you just took a test on? Nonpolar molecule.
CCL4.
CCl4 is great.
Another one.
Mm-hmm.
SO2.
Mm-hmm. SO2 is polar, it's got a lone pair.
What about
H2O.
H2O's got 2 lone pairs.
SBR.
SBR6, but y'all are working way too hard.
CLO3.
Got a lone pair. It's also got a -1 because it's a polyatomic ion.
What did you say?
I said, can you give me an example of a non-polar molecule?
pH3.
Huh?
pH3.
pH 3 is one of the exceptions because it turns out to be 0. But y'all are working way too hard trying to remember
HCl.
things. Huh?
I'm not looking at
It's
the
polar.
SiO2.
SiO2 is like CO2. It's going to be non-polar. But y'all are working way too hard trying to remember stuff that's non-polar.
SO3.
SO3 is, again.
Okay. SEBR. Boom.
It's a whole group of compounds that y'all are overlooking.
E.
What group was
That's true because it's a noble gas. I'm thinking something that will work besides the noble gases. Yes, I'll write the noble gases up here. Just a second.
Or
The what?
the whole people.
Is it a type of metal?
It's not a type of metal. Something we talked about today in the opening.
Noble gas.
What the?
Iguanas.
What about the diatomics and the Hector now owns 5 clear brown iguanas?
H2N2O.
What kind of bonds did they form?
Double, single.
Doesn't matter, but what kind of bonds did they form? And besides covalent, what'd you put in front of covalent? Exactly. Non-polar covalent. All right.
She said.
And you can put the noble gases there that Xavier said, because they're certainly going to fit there also. Okay. But the diatomics are great examples of ideal gases because they're non-polar covalent. So you're going to see your diatomics a lot. That's why when we were doing the conversion in the opening, I said make sure you remember them, because remember when I said the conversions were standard deductions? These little twos? I can't even begin to tell you the number of you who are going to lose points for those twos and not converting because of your diatomics on your quizzes and tests. The number of you who are going to lose those 5 points will be staggering between now and next week.
Astronomical.
It will be. And on the test too. You'll be surprised at how many of you will give me points back next week. All right, 5 properties of gases. Number 1, gases have the ability to expand. They fill their containers. Okay? Now, only gases have this ability. Sometimes students tell me liquids do, and we get to liquids and solids after this. Now, that would be so fabulous if liquids have the ability to expand and regenerate my cup of Pepsi after I drank it during second period. But unfortunately, I have not found a way for my cup of Pepsi to re-expand and fill that container during second period. I just haven't. So it doesn't happen. Gases are compressible.
But then why do people say that when they stick like a can of soda in the freezer, it explodes?
Because the water will freeze. It traps air between the water molecules and it will expand.
And that's when particles, they get cold and they separate.
Yeah, we'll talk about it when we do liquids after we do the gas laws, and I'll show you what happens because I'm going to talk about crystals and we'll talk about what happens to the ice.
Do you have a lab on this?
Can we do a lab on growing crystals?
Yes.
You know, I thought about y'all prom night when they had those little rock candy things on sticks on
Those
the
were
prom
good.
table. I was like, I wonder if anybody thought about those or ionic crystals that are on the prom table.
No, I didn't do that.
Who's thinking about school or prom?
I have a question. Do you know when or if we are going to get our keychains?
Somebody said they lost them.
They lost them.
No.
Somebody had, Miss B had somebody's on her desk. They should have gave them to the teachers.
Miss Love said that they weren't ready for prom night and they was getting them ready, but there is a box ready, but they want to get all of them and have them all at the same time so nobody complains to the teacher they might have not got their keychain.
That's good.
Well, that's probably why.
They need to hurry up. It's
Miss
been
Love and
almost.
Miss Willows are in charge of
There were literally only 5 done.
Miss
All
Love said she
prom.
got it, so she's not worried
The
about it.
same 5 were done. All prom. How does that work?
They said the
Take it
ones
forever.
that were closer towards like the beginning of prom, like between 7 and like 9, got their
I
stuff.
took mine early.
I couldn't even take mine because there was no one there.
And there was only like 4 on the table when I took mine.
Yeah,
And they were already done.
because they said between 7 and 9 was about the time they got all 5 of them finished. But anybody after that, it got busy and they don't.
Well, they didn't do their job.
All right, everybody done? All right. Now, in number 2, any questions about that one? Got it. Number 3. All right. Low density. Gases have a low density let me fix this formula here. Because, okay, if you look at the formula for density that we did way back at the beginning of the semester, all right, it takes up most of the space, but it has a very small mass, all right? If you look at what you do in math class, if this is the large number down here, all right, what happens when you divide by a big number? It makes it a very small number, right? That's why gases have a really low density. Because when you divide by that really big number, you get a really small number. Okay? Because the volume is just large. So you get a small density. Now, number 4 is a word that you guys have used before. All right? And a lot of us think about it in terms of liquids. Gases are fluids. They have the ability to flow. We're able to walk around through the room because the gas molecules can move and flow around us. When you get up to leave and go to third period or get up to put your calculators in the tub, when you get up to do that, the gas molecules will flow around your body. If the gas molecules didn't flow around your body, would you be able to put the calculators in the tub or go to third period? No, it'd be like walking into a wall. Molecules just wouldn't move around your body. It would be very painful to get up and move. All right. And the last property that all gases have is they have the ability to diffuse, which is why your classmates get all kinds of upset if you tend to pass gas in class. Because when you pass gas in class, does the scent just stay right here by you in your little sphere right here by your desk? No, it does not. Okay? Scents, gases, they spread. You learned in biology class when you talked about osmosis that they move from an area of high to low concentration, right? Same thing happens with just with diffusion. It's from an area of high concentration to low concentration. So the smell goes from where you're at and it spreads outward. Okay? Same thing happens with girls when they spray perfume. If you're sensitive to that kind of smell and odor and you don't really care for the scent, you spray it back there where Justice is at, and you spray the perfume because you're the girl sitting back there and you don't like the scent of the perfume, it's not going to stay where Justice is. That perfume scent will permeate and spread throughout the room. Okay? Diffusion works both ways, both good smells and bad smells. Okay? So if you are one of those people who tends to pass gas, and I have one, the fourth period, we just make him stick his behind out the side door. Yes. But we've worked out a plan. All right, so we're going to switch to math for the next 4, well, I guess probably about the next 6, 7 days. All right, we're going to calculate 4 mathematical quantities in our gas law problems. All right, we're going to calculate with volumes, temperatures, mass of moles, and pressures. Now, the first 3, we've already done this semester. So we reviewed those in the opening. The only one we haven't done is which one? The last one. So the last one is the one that we need to talk about before we can talk about any of the gas laws today. We got to talk about pressure conversions because we haven't done any of that. I could use an app.
I think we should reintroduce that into schools.
Nap time, like a brief nap period. Like,
Oh, we just start school late, like 9 o'clock.
I don't know, because if we had like nap around this fall, that would be good. Did you teach
When there were 8 periods, no, I know when there were 6 here, but
Did you
I,
hear better, or do you like the four?
It's easier than 4 periods.
How long
Honestly-
are the classes?
They're
Like
like
30
40,
minutes?
yeah, they're about 45.
honestly, I like the 4 better, only because there's less for y'all to keep up with. 6 was a lot.
We had
of classes.
six in
And most people gave homework, so it's just a lot to keep track of. So imagine if you were competitive now and you had AP classes or upper level classes and you were doing all that and people were giving homework, it would just be a lot to manage. So,
Right, because
You
we get
know-
homework every day, it'd be 2 days worth of homework.
I mean, I would not give as much as I do. We would do less than a day, so it might not be as bad. So we taught 6 classes and we were only in here for 55 minutes a day.
We got
So there were
homework.
pluses and minuses about it. Quizzes were shorter, tests were shorter. We did shorter things a day. Everything was scaled back. So some labs I couldn't do because you couldn't do it in 55-minute period. Like the salt lab I couldn't do back then because you couldn't do it in 55 minutes. You could do specific heat, you could do chalk, you could do some of those things. We can't do magnesium this semester because I don't have enough. I did it in the fall.
They still have 3 left.
I don't remember back then how many we had. We probably did have 3, but we did it a different way.
What
we
we
did
doing,
six.
just have a lunch. dude.
I only did that for about 3 years before we switched to the block. So I've never done 7 though. I know people who've done 7, and that's about 45-minute class. I can't imagine only having 45 minutes though.
So if you did, if there were
I mean,
8 classes,
you'd literally get here and be like, dang, the bell rang. Y'all just got to see. I can't imagine switching that often.
if you have 8 classes, you have 30 minutes each class.
I can't imagine having 8 classes. I just can't.
I can't handle the 4.5.
So,
That means like
Yeah,
having
how
all
much
your
tonight?
classes and
Huh?
way
Got homework
here.
tonight?
With every single day. If you really have.
Alright. so what is pressure?
It's that.
All right, pressure is force per unit of surface area.
Will this be on the test?
Remember, all of this is in multiple choice. Every bit of this so far will be in 10 multiple choice questions. All of the stuff that when we get down there, number 5, Boyle's Law, that will be in the board problems.
When we gonna have a quiz?
We will not have a quiz until we finish Dalton's Law. Quizzes are fewer and further between in this section.
So how long is this?
And you will only have 2, possibly 3 before the next test. 2 is a guarantee, 3 is a crapshoot. And then we'll test. So we'll do what's tomorrow, Thursday. Monday will be the first quiz problem. I don't think we can get to it by Friday. So probably Monday. All right, so how are force and surface area related to each other? Anybody know?
You say what?
How are force or pressure and surface area related to each other? Anybody know?
Pressure and surface area?
Mm-hmm.
The force,
The more
pressure,
you
on the
have, the more
surface.
surface area it covers.
All right. My girl should know this after Saturday night.
I don't get it.
All right, stand up.
Pressure on.
Girl?
Pressure on your feet.
Stand up. Should be an easy one for you to answer. Stand up. All
I
of it.
gotta pee.
I'll get it.
Oh.
Yeah, he'll start to hurt.
Stand up. Just stand flat-footed, Tiffany. Now go pee your pants. All right. So, what's your surface area?
Right.
What's touching the floor?
My shoes.
Your feet or your shoes, right? All right. So you know what the surface area is on your feet at the moment, right? What's causing the pressure?
Our body.
Your body weight. All right. So how do you change your surface area?
By putting more limbs on the floor.
Putting more what?
Limbs.
Okay. We don't have any more limbs to put on the floor.
You
We're
come
not
up on your
going
toes.
to.
You come up.
So how are we going to change your surface area? How did you
Change
change
on
it
your
on Saturday night?
Moving.
We got closer to
Sit
get
down.
Tippy toes.
You did what, Justice?
Stand on your toes.
They stood on their toes because they put what on? They put high heels on. So stand on your tippy toes like you did on Saturday night. All right. So what have you done to your surface area?
made it smaller.
Made your surface area smaller. Now what are you doing to the pressure on your feet?
Put more pressure.
It's more pressure. So what's the relationship?
The less surface area, the more pressure.
So what is that?
Area, the more pressure. Inversely
Invert.
proportional.
Very good. It's inversely proportional. All right. I imagine most of you took your heels off.
Yep.
That's fairly typical for prom night.
Put them under the table.
Okay, so,
I almost scared somebody was gonna steal it.
so remember that when I ask you on the test if you don't know. All right, pressure and surface area are inversely proportional. I've worked with two ladies here who always wore heels to teach in. Always.
Who?
Miss Clements and Miss Brown and Miss Phillips. Both of them have had foot surgery. They've walked on cement with tile for years. One was a runway model and became a teacher, and the other one was just a teacher, wore heels and walked on the cement tile for years. Both of them had to have foot surgery. You will never catch me in that here.
I walk barefoot when I walk with shoes on.
Again, wear shoes of some kind if you don't want to have foot trouble down the road.
Yeah, and Miss Hudson said that you could get worms or warts on your feet. I just don't like shoes because of the dirtiness.
I don't know where y'all be walking.
It don't matter where you are.
If you go to school, do not go in a communal shower, bathroom, anywhere without some kind of flip flops on.
I don't even want to be
Yeah,
on a
because-
hall.
So you remember Miss Jones used to do it? She used to walk.
Yeah, she was always in my shoes.
I'm gonna wind up with some kind of weird foot fungus.
Her feet was
Ah.
green that one day we looked at them.
Now, the 5 pressure units that we're gonna use. All right, and we're gonna use all 5. These are the 5 pressure units we're gonna use. We're gonna use atmospheres. We're gonna use millimeters of mercury. We're gonna use torr. We're gonna use pascals. And we're gonna use kilopascals. Okay, all 5.
5 pressure units.
Yep, these are the 5 pressure units. These are the abbreviations, and these are what they stand for.
Mercury.
Now, ATM, half of y'all are gonna say atoms, and I will correct you every single time. They are not atoms. They have never been atoms. They are never going to be atoms. Atoms does not have an abbreviation. ATM stands for atmospheres. Okay, millimeters of mercury is based on the barometer.
Oh my God.
All right, torr is Torricelli. PA is Pascal.
With jelly sound place.
And KPA is kilopascal.
Is that P supposed to be?
Capitalized, yeah.
You said these are the 5 pressure.
Units.
Which one's blood pressure?
Which one is what?
Blood pressure.
Which one is pressure?
No, never mind.
She said, which one is blood pressure?
Blood pressure. Any of those can be used. These are more used for atmospheric pressure. I don't know exactly which one they use for blood pressure. In the United States, we use inches of mercury to read atmospheric pressure. These are going to be metrics. Now,
Why do they call it mercury?
yes, the first barometer was done with mercury, and so that's why it's done with millimeters of mercury. And Torricelli is the Italian scientist who built the first barometer, so they named the unit after him. And then Pascal did a lot of work with gas laws and with this, so we named the unit after him.
Have we explored all the planets?
Have we? Oh, well, truthfully, I've got no idea. Now,
So is Pluto a planet or a star?
you know, at one time he was bumped out, but I thought they put him back in, so I can't say. I don't keep up with that.
I just thought it
Now, these are how they're related to each other. The good news for y'all
You gotta remember.
is 3 of them are on the reference table. Okay? These 3 right here are on the reference table. Okay? Those are on the reference table. This one here is not on the reference table. You have to remember it, or you can make the conversion from KPA to PA. Yeah. You can do it either way. I don't care. But you have to be able to get PA. Okay?
Can we do like 1.01 or do we have to go the entire?
I will tell you the reference table only has 101.3. Okay? it is not going to significantly impact your answer. I tend to use 101.325 because that's the way I learned it in high school. So I don't care as long as you have 101.3. Now, the nice part about these conversions is, what do you notice about all those atmospheres? They're always going to be what number? 1. So, when we have to worry about, like we did with moles, with the atmospheres changing to a different number, the answer is no. They're always going to be a 1. All right, does everybody have the numbers? I need to wait.
Yeah.
Okay.
We just got that new thing. You should be giving quick information.
Sounds like me. I'm not like that person.
Precisely, you were.
Yeah, what?
I'm not like that.
I don't like
Is it?
What are we talking about?
Miss
Miss Ruffy.
Oh,
Man,
what?
y'all should see her at prom. When they was playing this one song, she was getting. I was like, oh my god.
What she wear
I
to
have
prom?
never seen her move.
What she wear to
She wore
prom?
her normal outfit.
Same thing she
Like
wears.
that
She
bird.
wore some comfy pants and a t-shirt.
At least
And
she
her
got
little
like
Birkenstocks.
Wouldn't expect anything.
All right. So, if I asked y'all to do 475 millimeters of mercury to PA, would y'all be okay with it?
Yeah.
No.
Okay. So, some of you would say millimeters of mercury to ATM, which would be fine. And then you would go ATM to PA because that's the way these are set up. PA is equal to ATM, and then ATM is equal to millimeters of AG, mmHg. Nothing wrong with it. But the point I was trying to make a second ago is ATM ever going to change from 1? No. So, is there any need to have to go through atmospheres? No. So, oops, I left out now. So, if you want to, you can actually skip that step and go directly from mmHg to PA if you would like to. You can choose the chart that you would like. Let me give myself a little more room there. You can choose the chart that you would like to do. You can do this chart or you can do this chart. I will tell you, I am not going to choose this chart ever. I am always going to choose this chart because ATM is going to be a 1. I'm going to make life easy on myself and I'm going to do less work. Okay? Now, you can choose to do it this way. Oops. If that's what you saw and that's the way your brain processed it and that's the way you wanted to do it, go for it. Okay? I'm into simple. I'm into less work. So, what number is in front of
76.
mmHg when I cruise back over here? mmHg has 760, right? So I'm going to put 760 in front of mmHg. What number is in front of PA? Okay, so I'm going to put it right here. 1.01325 times 10 to the 5th. And now I just need to put that in my calculator the way we used to be able to do it. Now, I picked that one because I wanted to make sure everybody could still do their exponents. So, 475, oops, 475 times 1.01325. How do I put that exponent in again? Second, and then EE, right? No times 10, no times, none of those things, just second and EE. And then I put 5 I always hit enter and divide 760. Now I get this 63,000 number.
Yeah.
All right, I'm going to put it in scientific notation because I'm not leaving that 63,000 number. So 6.33 times 10 to the 1, 2, 3, 4. 4 and PA.
Do we have to change it?
If you have a number that big, you should change it. Okay, you should not leave that giant number out there. You should go ahead and change that. Does that make sense? Everybody okay with that? Okay. Anybody struggling? Debating.
Please do.
Do we own
Or what?
it?
All right.
Oh, here you go.
Huh? After you have that.
This was like that. Yeah. I put in scientific.
You just messed it up when you changed it. Punch it in again and you'll get scientific notation. If it does that, just punch it in again.
Outstanding.
I was right.
Outstanding.
Yeah, probably the last 10 minutes.
What's that? That's a good thing.
Oh, let me take
I was gonna say earlier, I love you.
Why put my pins in?
No, if I got it, if I
Take a note, I gotta have all my pins, not just one.
Sure.
All the same color, I'm never gonna.
He won't.
Alright,
Should have been fit.
convert 1 through 10.
No.
Yes.
No. Is it amazing?
Is that or we're gonna do Moore's Law?
Okay, never mind.
No, it was that.
Mark, just comparing here.
Oh.
I'm just fixing you. Abraham.
Isn't the O? Sorry,
Is it what?
I was gonna say,
Oxygen?
after, no, after the decimal, the first O is just placeholder.
After the decimal? Is there a number before the decimal?
No.
And the first, after the decimal is placeholder, that's correct. Have a question?
Hmm.